So I'd like to thank Professor for inviting me for this seminar. It is an honor and pleasure to give a talk in KAIST. So the title for today's talk is Combinatorial Formula for Information Flow in a Network. So basically the idea is that we look at a network, where network means we have a weighted graph. Weighted graph simply means that we have vertices, which are often referred to as nodes, and the edges are weighted depending on the level of interaction between two nodes, where two nodes can be considered as participants or people communicating, so to speak. And the notion of information flow was introduced in the work of Stevenson and Zelen in 1989. Stevenson is a retired professor at the School of Public Health at Harvard University, and Zelen was a professor at the School of Public Health, and Stevenson is a professor at the anthropology department at Harvard. And they were trying to study, so to speak, who's the most important participant in a network. And in deciding who's important, they introduced the notion of information centrality. So information centrality basically means that which node is most capable of disseminating or receiving information throughout the whole network. And depending on who's most capable of receiving and disseminating information, they decided who's the most important node, so to speak, who's the most influential node in the network. So the basic mathematical setup is by means of graph theory. So we'll let G be a weighted graph representing a social network. So in this case, a social network simply means information network. So in this case, as I just mentioned, the nodes represent people or the participants, and the weight of each edge, for example, is a frequency of interaction. So the more you interact, the weight goes up between the two nodes. So we'll see a lot of examples like this later on. And the basic idea is then, in order to compute the amount of information contained in a simple path P, where P is a path connecting, say, the vertex I and J, then the amount of information that's contained in I sub P, in the simple path P, is simply the reciprocal of the length. And the idea is that the longer the length of the communication, the less exact the communication is going to be, or there will be information loss, so to speak, in the course of traveling through the simple path. So the amount of information is defined to be, in this case, the length of P and the reciprocal of that. Now what happens if we have more than two paths? So for example, we have two vertices, and there may be multiple paths like this. So in those cases, we simply add the amount of information that's contained in each of these paths. But obviously it does not solve the entire problem, because we may have some other different kinds of configuration of the graph. So we'll take up those things later on, as Stevenson and Zelen did. So using their notation, we'll use I sub AB and I sub BA, which are equal, because in this case the graphs are not assumed to be directed. It's a simple graph with weights with the real numbers. So I sub AB is equal to I sub B8, and that's the information contained in all possible paths between A and B. And that alone is already very difficult to compute, but here's what they did. So the way they computed the amount of information is, first of all, they computed the Laplacian matrix of the weighted graph, which I'll explain what it is in a minute. And then they also added the J matrix. So the J matrix is what's called all ones matrix, which means that every entry in that matrix is 1. So Laplacian matrix plus the all ones matrix turns out to be invertible, as I'll explain later on. So you take the inverse of that matrix and call the ijth entry of the matrix G sub ij. And here's this interesting combination of those entries. So the two diagonal entries, G sub A and G sub BB, minus two off-diagonal entries, and then take the reciprocal of it, and that turns out to be the information. Now this is a very mysterious quantity, and what we're trying to do today is to understand this quantity combinatorially. And as it turns out, the understanding this quantity combinatorially in terms of the basic fundamental invariance of the underlying graph turns out to be an interesting object. And as we'll see later on, that the result turns out to be closely connected what Professor Thomason did last week. So here's an example of how to compute the information. Suppose we have a weighted graph like this, 4 vertices and 5 edges, and the red ones are the weights. So the weight 2 connecting 2 and 4 means you can think of this as people number 2 and 4 were interacting twice, and all the other ones just interacting once, so to speak. And by the way, this kind of network study was done in order to study how the AIDS disease was spreading among the AIDS patients and so forth. So in those cases, the number represents the number of interactions between the AIDS patients and so forth. So in this case, I sub 2, 4, which means the information flow between 2 and 4 turns out to be 3. And here's how it's computed. There's an obvious path between 2 and 4 of weight 2, and there's another path via 1, and another path via 3. And we notice that those 2 paths via 1 and 3 have length 2. So the actual amount of information that's contained in those will be 1/2. Each of these contributing 1/2, so that's where we get 3 for the information. And the information between 1 and 3, so we look at the paths 1, 4, 3 and 1, 2, 3, both of which have length 2, so they're contributing 1/2 each, and that's where we get 1. So the question is, what about the middle path, which acts as a bridge? And it turns out that because of the symmetry of the situation, which means that these 2 paths and these 2 paths have equal weights, and the bridge does not introduce any information flow because of symmetry. Now that fact is all captured in this equation, and obviously it's not obvious why it would not do such things, but we'll see later on what's happening. So again, all the other ones turn out to be 12/7, which is computed using the Stevenson and Zelensky's formula for the information flow. Now, so that's the intuitive introduction to what information flow is about. So now back to the original question. We want to understand these numbers, these information flows, combinatorially. So what objects or what invariants about the graphs are going to help us describe what these numbers represent? So it turns out the most important invariant or concept that is necessary is called the spanning tree of a finite graph. So we'll take a quick review of what a spanning tree of a graph is. So a finite graph simply means that we have a finite number of vertices, and if you like, we can think of this as having also a finite number of edges. So a spanning tree means that every vertex of G also appears in the spanning tree T. And also T has to be a connected subgraph, and T has no cycles. So that's what we call the spanning tree of a graph. So here's some examples. So here's a graph G where all the vertices are labeled. And then an example of a spanning tree. Will be something like this. So the first one is a spanning tree. It has all the vertices appearing in this subgraph, and the graph is connected. And
is it different from maximal graph?
It's the same thing as a maximal graph with no cycles. Maximal contractible.
Yeah, maximal tree.
Yes, it's the same thing as a maximal tree. Yes. But what's not a spanning tree will be something like this, which is cycle-free but not connected. And a graph like this is also not a spanning tree because it contains a cycle. And it turns out that all of the spanning trees have the same number of edges, which is n minus 1. Just like in this case, we have 4 vertices and 3 edges. So the number of spanning trees is a very important invariant of a graph, so we'll use a special notation for that. So K of G will be referred to as the number of spanning trees, and it's called a complexity, or sometimes it's called the tree number of a graph. And in this talk, we'll refer to this as the complexity of the graph. And it turns out that G is a connected graph if and only if there's one or more spanning trees. So that's the same thing as saying the complexity is strictly positive. And one example of a complexity is that when we have a complete graph simply means that it's a graph where every pair of edges, pair of vertices has an edge, and the number is n to the n minus 2. And there's an interesting deletion and contraction recursion about how to compute the complexity. So complexity of a graph can be computed in this following manner, where K set minus E simply means deleting one edge of a graph, and G slash E simply means contracting an edge to a single point. So those two graphs are called minors of the original graph G, and if you compute the complexity of those two minors and add, that is also the complexity of the graph. And the reason behind that goes as follows. We can classify the set of all spanning trees into two separate groups. One is those that contain a given edge E, and those without the given edge E. So those that do not contain E also turn out to be the spanning trees of the deletion. And those that contain a given edge E turn out to be the spanning tree of the contraction. So that's how this kind of deletion and contraction actually works. Now in this case, there is a condition that the edge that you're looking at is not an isthmus. So isthmus is also another word for bridge. So bridge means that it's an edge where you delete, it separates the graph into two different components. So as long as E is not that kind of bridge, this deletion contraction recursion works. So now, a weighted graph, as I mentioned several times now, it's a graph where we assign a real number to each edge. So we assign a number to every pair of vertices in the graph. And the nice thing about the weighted graph is then we can regard every graph as a weighted graph. For instance, in a multigraph, we can simply regard the weight of the edge being the number of edges between the two vertices. So every graph can be regarded as a weighted graph. And the main important tool for understanding the combinatorial interpretation of the information flow will be the Laplacian matrix. So for the definition of the Laplacian matrix, we'll go right into the example instead of looking at this words. So back to the same example as before. Now the matrix D, which stands for the degree, means that it's a diagonal matrix where the first entry 2 refers to the sum of the weights that are connected to the vertex 1, and the second entry 4 refers to the sum of the weights that are connected to 2, which is 4 in this case, and the same thing with the third and the fourth entry. So it's a diagonal matrix, and the adjacency matrix refers to the weights between two vertices. So for instance, this entry here, 2, refers to the weight between the vertex 4 and 2, which refers to this number here. And the number right here refers to the weight between 1 and 2. So both of these matrices are symmetric matrices, as you can see. And the Laplacian matrix is defined to be simply the matrix D minus A. And the reason why we're looking at this matrix, Laplacian matrix, is that this matrix alone keeps track of everything that is contained in the graph. And if you have a graph, you can always get the Laplacian matrix, or if you know the Laplacian matrix of the graph, you can also recover the graph. So it goes both ways. So let's look at some of the important properties of the Laplacian matrix.
It's abstractive. Why don't you
What is
You
it?
add them. I
What?
mean, you are subtracting too.
Oh, why do I add them?
Yeah.
So that's what I'm about to talk about. So there's a very important reason why we want to subtract them instead of adding them. So first of all, so L of G, the Laplacian matrix is symmetric with non-negative eigenvalues. So having non-negative eigenvalues is a well-known fact. And let me skip the explanation of that part. Let me just say that there's another way to obtain the Laplacian matrix as a product of another matrix that is associated with the graph with its transpose. So from linear algebra, we know that every matrix times its transpose is always, the eigenvalue of that kind of matrix always have non-negative eigenvalues. So that's where this fact comes from. And L of G is balanced. Now, balance simply means that the sum of the entries in each row and each column turn out to be 0. So that's what we'll call a balanced matrix. Now, if a matrix is balanced, regardless of whether it's a Laplacian matrix or not, its determinant is 0, because having row sum and the column sum 0 means that if you add all the columns and the rows, it becomes 0. So the rows and columns are linearly dependent. And not only that, it's an easy exercise from linear algebra that in that case, every cofactor of that matrix is actually the same. Now here's the main reason why we want to subtract instead of adding. So when we subtract, we get a balanced matrix. So every cofactor is the same. So the question is, what does that cofactor represent? And the answer is given by this matrix tree theorem. So for any ordinary graph, every cofactor of the Laplacian matrix is actually counting the number of spanning trees. So that's a very surprising and intriguing fact. And I listed the proof very briefly. So let me just touch on this for 1 second. So the proof goes by induction on the number of edges. So if we call lambda d to be the cofactor of the Laplacian matrix of the deletion, which has one less edge, obviously, and then lambda sub c as to be the cofactor of the contraction matrix, then by, again, a linear algebraic argument, it's very easy to show that the cofactor of the original Laplacian matrix of the graph G is the sum of these two. So now this fact is a fairly trivial fact to check. But what's also true by induction is that lambda sub d is the complexity of the deletion, and lambda sub c is the complexity of the contraction. But then we saw that the complexity follows the deletion contraction recursion. So that's where the equality comes from. So that's a brief proof of why every cofactor of the Laplacian matrix is a complexity of the graph, and that's a very important fact. So in the case of a weighted graph, we'll define the complexity of G to be any cofactor of the Laplacian matrix. Now, in the case of weighted graph, where the weight can be any real number, it doesn't even have to be integers. It could even be negative numbers, or it could even be irrational numbers. So in those cases, counting the number of spanning trees does not make any sense. So in those cases, we'll simply define the complexity to be any cofactor of its Laplacian, and it is consistent with the number of spanning trees of the general graph. So this is an extension of the already known notion of complexity. And here's the main theorem that will be used in deriving the combinatorial interpretation of the information. And this theorem was first introduced by a physicist named Temperley in 1964. And he was the one who studied not just the Laplacian matrix, but rather Laplacian matrix plus the J matrix, all ones matrix. Now, one awkward thing about the Laplacian matrix is that its determinant is 0, so which means the matrix is not invertible. And also, if you want to compute the complexity out of the Laplacian matrix, you have to compute a cofactor, which means you have to delete one row and one column. So that's the awkward part. But what he did was, instead of deleting any row or column, let's just add this simple matrix and compute the determinant. And what it turns out to be is the complexity of the graph times n squared. And in this case, the meaning of n squared is the sum of all the entries in the J matrix, because J matrix n by n all ones matrix. So that's the main theorem that we'll be using. But it turns out that as it stands, it's not going to be sufficient. So what we'll do is we'll generalize this to the following linear algebraic fact. So it turns out, as we'll see in the proof of this theorem K1, the reason why this actually works is because of the following fact. The first matrix is a balanced matrix, and the J matrix is actually a rank 1 matrix, and also n squared that appears here is the sum of all the entries in J. So let's call the sigma to be the sum of all entries in U, and any cofactor of LG was K of G, so we'll just call that cofactor of this balanced matrix M as mu. So if mu and sigma satisfy all these conditions, then an analog of Templey's result also works. So that is the generalization of Templey's result. And as you can see, this is analog of the matrix tree theorem. In fact, in some sense, it's easier because you don't have to arbitrarily pick any rows and columns. So let's take a look at a quick proof of this fact, which is quite nice, and I think it's a quite pleasant proof. So this is what we're trying to prove. And so determinant of the sum of two square matrices. So let's think of a matrix M and U as made of columns. So in this case, matrix M has columns C1 through Cn, and matrix U has columns D1 through Dn. So this is a determinant of another n by n matrices where each column is the sum of columns of each matrix. But using the multilinearity of the determinant function from linear algebra, we can write this as a sum of determinants where each xi in this case is either ci or di. So this step is, again, not immediately obvious, but not a difficult exercise from the point of view of multilinearity of determinant function. And we have 2 to the n such determinants because each x of I is allowed to be either ci or di. But it turns out that not all of 2 to the n terms in this summation contributes. The reason is the rank of U is just 1. So as soon as you have 2 columns from the matrix U, the determinant becomes 0. So the only ones that will contribute to this summation is the ones that has only 1 column from U and all the other ones from the matrix M. But then when you actually expand the matrix, expand the determinant, using the entries in D sub I, it precisely becomes the cofactor of the matrix M, and sigma sub I is simply the sum of the entries in the ith column in this matrix. So when you add them up, we get the result. So this is a nice application of multilinearity of determinant function. So from this point of view, we get the Templey's result as a corollary to this theorem K1. So we'll be using this theorem later on in deriving the interpretation. Now the second important notion that we'll need is a contraction of a graph, which is quite intuitively clear. So we'll start with an example again. So same example of a graph before, and we'll denote the contraction contracting two edges into one vertex as G sub AB. So in this case, G sub AB is a graph obtained from G by identifying two vertices A and B. So here's the result of G sub 1, 2. So that means 1 and 2 are going to be contracted into a single point. Now, we'll describe all the resulting graph again as a weighted graph. So in those cases, this weight 1 and this weight 2 will be added to give a new weight 3, and all the other edges remain the same. And here's an example of contracting the vertices 2 and 4. So in those cases, the edge 2 and 4 disappears, and the new weights 2 are the result of adding 1s here and then 1s there. So they're added. And also we can think about the Laplacian matrix of the resulting contractions following the definition of the Laplacian matrix of the graph. But it turns out that if the Laplacian matrix is what you're really concerned about, then we don't have to go back to the graphs, but rather we can do this just by doing some row and column operation to the Laplacian matrix. So I'll call that matrix contraction, which is simply trying to give a linear algebraic version of what the graph contraction is. So the contraction of a given graph, given matrix, square matrix, is obtained by replacing the bth row by r sub a plus r sub b. So r simply means the eighth row and bth row, and c simply means the column number b and column number a, and so forth. So replace the bth row by r sub a plus r sub b, and replace c sub b by c sub a and c sub b. So those two operations correspond to weights being added. And it has to be done in a symmetric way, so that's why we do the row operation and the column operation. And then deleting the eighth row and eighth column, so that just means that two vertices are identified into one, so you have to abandon one of them from your list of vertices. So that's, and I just listed one example. So this was the Laplacian matrix of our original example, and here's the result of applying these two row and column operations. And then the last one is simply deleting the first row and first column. And if you recall, that is the same Laplacian matrix of G sub 1, 2, so to speak.
One question, please.
Yep.
Previously, it becomes 0, but later it becomes -1.
Which entry are
The third column.
-1 is added to 0, so -1 you drop first column, so it becomes -1.
You just don't remove the row and column?
He's
Yeah,
removing
remove
first
the
and
first
first column and
first
row.
one, first column?
Okay.
Yeah. So here are some of the properties of the matrix contraction. And one obvious property is that the Laplacian matrix of the contraction of the graph is a contraction of the Laplacian matrix. So the contraction of the graphs and contraction of the matrix, they commute. And that's exactly why we actually started out to define a matrix contraction. And it turns out that the addition and the matrix contraction also commutes, which is fairly obvious because row operations and column operations can be done in either order, either adding first and then doing the contraction, or contraction first and then adding. And also, an important point is that if the matrix M was balanced, which means if the row sum and the column sum are 0, then the same property holds for the contraction as well. So in that case, if M was balanced, then the every cofactor of its contraction matrix also is the same. And there are some other properties, such as if the sum of the entries in the original matrix was n, then the sum of the entries in the contraction is also equal to n. So that it also preserves the sum of the entries. And this property is not terribly important for us, so we'll skip this part. So the lemma is that the determinant of the contraction of the Laplacian matrix plus the J matrix also turns out to be very simple. It's again n squared times the contraction of the complexity of the contraction matrix. And the proof of this fact is simply relisting the properties that we saw about the contraction matrix in terms of the Laplacian matrix and the J matrix. So once you follow those properties carefully, it's not very difficult to see that this equality holds. So the interesting thing about this result is that simply by using the contraction matrix of the sum of these two, we can again recover the complexity of the contraction graph. Now this proposition is a rather technical fact which we'll be using in a minute. So the content of this proposition is as follows. So suppose we have a matrix B, and suppose we computed the determinant of the contraction of the matrix. Then can we describe the determinant in terms of anything about the original matrix? And it turns out that the determinant of the contraction of a matrix has this expression. So notice this expression is quite similar to the expression for the information flow given by Stevenson and Zelen. And the proof of this fact is quite technical, so I'll just point out a few things, and I'll go to the next slide. So this is done simply by first switching row number A with row number 1 and row number B with row number 2. And then it's much easier to prove this fact when A and B are 1 and 2. And then once you get the result, you can switch everything back. But we have to be careful when you're dealing with determinants and switching, because if you switch it once or odd number of times, the sign changes, but it turns out in this case, everything will be done twice. So there will be no danger of confusing the sign in the end. And that's the main reason why we have the result once we have the result at A equals 1 and B equals 2. So here's the main theorem of the first part. So the statement goes as follows. So let's let G be a finite weighted graph of order n, and we assume that the graph is connected, or in the case of weighted graph, the complexity is non-zero. And let's define B to be the Laplacian matrix plus all ones matrix, which is what Stevenson and Zelen use in their studies for information flow. And now we know that this is invertible because if you recall the temporalist result, the determinant of this was n squared times the complexity of the graph. So if the complexity of the graph is non-zero, then the determinant of this is also non-zero, so we can obtain the inverse matrix. And here's the interesting part. The interesting part is using this matrix and entries, let's form the left side of this expression. Then it turns out it is a quotient of the two complexities. The complexity of the contraction graph and the original graph. So let me point out the proof as follows. So let's just recall how we compute the inverse matrix. So in order to compute the inverse matrix, we need to first compute the adjoint of the matrix. And each entry of the adjoint, let's call that beta sub ij. So beta sub ij is simply the cofactors of the matrix B. So that's the definition of beta sub ij. And we know that G sub ij then is going to be beta sub ij divided by the determinant of B. But we already know what the determinant of B is by the temporalist result. So that's n squared times the complexity of G. So when you form this expression, we factor out 1 over n squared times the complexity of G plus all these terms. But then by the previous proposition, it's the determinant of the contraction of the matrix, and that also equals n squared times the complexity of the contraction graph. So we get the result. So back to our original question that we set out to do. The given network represented by a finite weighted graph, let's let I sub AB be the information contained in all possible paths, as defined by Stevenson and Zelen. Then the combinatorial interpretation of the information contained in all possible paths between two arbitrary nodes is nothing more than just the ratio of the complexity of the original graph and the contraction graph. So that is the combinatorial interpretation. And the proof is immediate because we know that we're still borrowing Stevenson and Zelen's expression here, but we can simply rewrite 2 times C sub AB as these, and then using the previous theorem, we get the following interesting interpretation. And those of you who were listening to Professor Thomason's discrete math seminar last week probably noted that this came up. And I'm about to show you why this is not surprising that this should come up. in this context as well. So Professor Thomason in 1990 showed that the effective resistance in an electrical network, where electrical network is represented by a weighted graph, and the weight of the graph is given by the resistance between two nodes. And it turns out to be very similar, in fact identical, except that one is the reciprocal of the other. So the result that we also have is the information flow that was studied by Stevens and Zelen also turns out to be nothing more than just the reciprocal of the resistance in an electrical network. And the reciprocal of the resistance is what we call the conductance. So I will show you how to arrive at this result without any reference to the information flow or Thomason's work that's purely graph theoretical. So the reason why that kind of expression comes up is because we want to understand what's called the discrete Laplace equation. So discrete Laplace equation, when we're given a weighted graph, is an equation like this, using the Laplacian matrix times vector x equals another vector y, and usually the vector y is given. And the Laplacian matrix is also given, so we're trying to solve for x. So that's what we're trying to do. And it turns out solving for x may not be easy, or it may not give a unique answer because the matrix LG is not even invertible. Well, what's also true is that the y vector is perpendicular to all 1's vectors. So the boldface 1 means a column vector where every entry is equal to 1. Then this L of g plus j times x equals y also implies the L of g of x equals y. So what that means is that instead of solving this equation, we can solve this equation. And this is much easier to solve because L of g plus j, now we know, is invertible as long as the graph G is connected. So, and here's the proof, and the proof is very simple. So let me just point out one reason why this works. So once you have this equation, we can multiply both sides by j, and then eventually you can show that j of x really does not contribute anything. So L of g times x is equal to L of g plus j times x, and which is equal to y. So in summary of this discussion, then the solution to the discrete Laplace equation can be obtained by using the, so to speak, the augmented Laplacian matrix and take the inverse of it and multiply both sides by that. And in some sense, that's why this matrix was used in Stevenson and Zelen's work in computing the information flow. So let's take a look at the Kirchhoff's law, which was also discussed briefly last week. So in this case, G is a connected electrical network of nodes and resistance, R sub ij. So in this case, we assume that there are n nodes, and between each pair of nodes, there is a resistance. Now, instead of using resistance as its weight, we'll use the reciprocal of it, which is called the conductance between I and j. So we get a weighted graph. So once we have the weighted graph, we can also get the Laplacian matrix of G, just like what we did before. Again, L is symmetric and L is balanced, and all those properties are all there. And let's call V sub I be the electrical potential. So electrical potential is measured at each node, and we don't need to really understand what they are for our purpose. And we also denote capital I sub I to be the net current flowing into the network at a given node. So one condition about I sub I is that the sum of all the electric currents throughout the network has to be 0, because once something is going in, that has to come out. It doesn't have to go in through one single node. It can go into multiple nodes, but then it has to come out. So that's the assumption. Now, one main difference between last week and this week is that last week we assumed that the the current flow at each node is 0. But we're not going to assume that, because at some node, the current has to flow into the node, and at some node, the flow has to come out of the node. So here's the Kirchhoff's law in a single linear algebraic fashion, in a version. So I sub I measures the net current that's flowing into the given node. So that is measured by first computing the potential difference between the ith node and the jth node. And C sub ij, which is a conductance, is what encourages the current flow. So the potential difference times the conductance gives you the current flow from I to j. So if you want to measure the net current flowing into I, all you have to do is simply add those currents as you fix I, but j varies from 1 to n. So that gives us the net current that's flowing into the ith node. But then if you rewrite this into a single matrix equation, that's precisely what we get. So this is an example of a discrete Laplace equation, so to speak. Now, here's how physicists try to solve this equation. And obviously, it's very easy to imagine that people have been trying to compute the resistance or conductance given a network. So it's not surprising that this was studied by many different fields of natural science, so to speak. And the way they did was, the idea is similar in that they want to find an invertible matrix that will give them an answer. So what they do is, instead of using L, they add epsilon times I, where epsilon is a small positive number, so that this matrix is invertible. So they invert the matrix, but then later epsilon has to be sent to 0 in order to get the answer they want. So in this case, the solving for this system means, because the L is given and I is also given, solving the system is finding the potential. So that's what we're trying to solve here. But as we saw a minute ago, we see that this condition is equivalent to saying that this electric current vector is perpendicular to all one's vector. So in that case, using the lemma that we just discussed, we can simply multiply by L sub j, the inverse of that matrix, and multiply on the right-hand side, and that also is going to give us the solution. So I think this is a much nicer looking solution than this one, in that we don't have to send anything to 0, but also this allows a lot of different combinatorial interpretation. So I'm just going to call this matrix, which is L plus J inverse, the combinatorial Green's function. And the Green's function is the name of this function as called by physicists. But since our new version of the Green's function has a lot of combinatorial really interesting properties, we'll call this combinatorial Green's function. So, so here's how we solve the discrete Laplace equation in the case of electric resistor network. So we assume that the current is flowing into the 8th node, and the current is flowing out of bth node, and the amount has to be the same. And at all the other nodes, the net current is going to be 0. So the I vector has 2 entries, 1 and -1, and all the other entries is going to be 0. So it's a very simple looking column vector. So once you solve for the potentials using this, the effective resistance can be computed as follows. So the effective resistance between A and B is the potential difference between the 2 points divided by R. And as we all know from high school physics classes, the potential is the resistance times the current. So this is just a different version of that. So when you solve for V out of this using this combinatorial Green's function, you can easily see that V sub A is going to be G sub AA minus G sub AB times I, and also similarly for V sub B. So if you compute R sub AB, we get precisely the same exact expression as the information flow in the information network. So this gives us a proof of Professor Thomason's expression for the effective resistance that is purely linear algebraic, so to speak. So in this case, instead of computing the resistance itself, we are interested in the reciprocal of it, which also corresponds to the information flow. So this is the proof of Thomason's result for the resistance, and also this shows that the information flow that's studied by the social scientists turn out to be nothing more than the resistance or conductance in an electrical network. So I think I'll stop here. Yes.
Thank you very much. Do you have any questions?